All right, so we looked at a general addition rule, so now I'm going to show you the general multiplication rule. All right, remember we said and means multiply. So I'm just going to expand this definition just a little bit. So if I have events A and B, and I want to multiply them, I take probability of A, the first thing, and I multiply, terrible multiply symbol, times the probability of B, but I acknowledge that A has already happened. Now this one is just a little bit hard for students to wrap their brains around. So I'm going to show you a really simple example to help you understand what I mean when I say this part, the B given A. So just my little example, let's pretend we're on a game show and we have 8 prizes. There are 2 cars, 3 TVs, and 3 iPads. And in this particular game show, you're just randomly selecting the prize. So let's say the first contestant wants a car. So let's figure out the probability the first contestant can win a car. Well, there are 2 cars out of 8 prizes. Okay, we've done that before. Now, what if the second contestant came up and the second contestant also wanted a car? So now we're talking about the first person winning a car, and so we're going to multiply the second person also winning a car. So the first person wins a car. That's 2 out of 8. We already discussed that. And means we're going to multiply. And now I need the second contestant to win a car. Now in the past we've just said, well, it's always the same. So it would be 2 8s times 2 8s. But this is different because the first contestant already won a car. So things have changed. That's what I mean by this given A. Given the first person won a car, that means that car is gone. There's only 1 car left, and there aren't 8 prizes anymore. Now there are 7 prizes. Okay, things have changed. So now the second contestant winning a car would be 1 out of 7. There's 1 car left out of 7 prizes left. So that's 2 out of 56 or 1 out of 28. Okay, so this is all that I mean when I say this B given A. Okay, just keeping in mind that event A kind of changed things. Person 1 winning a car changed the probabilities for person 2. That's what I mean. All right, so I told you that we'd take a closer look at independence, because I keep tossing this word around. It might be driving us crazy. Independence, the outcome of one event does not influence or change the probability of another. This that we just looked at is a great example of not independent. Why? Because person number 1 winning the car changed the probability for person 2. Independent would be if that didn't happen. If I had a cool game show where I kept restocking the prizes, so you always had a 2 out of 8 chance of winning a car. Okay, that's independent. So 2 events are independent if the probability of B given A is the same as the probability of B. This is not on your formula page, okay, this definition. So this is something you just got to work out in your brain to help you remember. What this says is knowing A happened doesn't change anything. Knowing A happened doesn't change anything. A could happen, and I still get the same probability for B. So let's see an example of using this rule. So hopefully we remember seeing our tables like way back in chapter 3. Ooh. So here I have male, female, so I'm representing the variable gender. And it looks like there's 17 males, 19 females. And then I'm kept track of whether or not they're wearing jeans or something else. Okay, so that could be just other material, could be a skirt, I don't know. So this is the variable attire. And I might ask the question, what's the probability we get a male? Okay, just in general. Well, there are 17 males out of 36 students. Cool. Different question. What's the probability I choose a male given they're wearing jeans? So if I know someone is wearing jeans. Now, I know I did show you a formula for calculating conditional probability, but when it comes to tables, I don't like to use that. I like to do whatever's easiest. So I'm going to go back to my chapter 3 ideas. Given that they're wearing jeans, I already know they're wearing jeans. That means I'm only looking at the jeans section. Well, how many are male? 12 out of 20. Okay. Make it easier on yourself. Just focus in on the piece of the table that's relevant. So the question is, are gender and attire independent? If I know someone is wearing jeans, would that change what gender they might be? Now, I know every instinct of you is crying out, of course gender and attire are independent. Being male, female does not mean you wear jeans or not, but keep in mind we are using this particular set of data, and if I just stare at it, wow, more than half of the males are wearing jeans, and more than half of the females are not. Okay, so I'm focusing on this data set. Now, the way I test for independence formally is I use this rule. I ask myself, let's see if I can get these both on the screen. Does the probability of, let's see, some B given A, well, maybe that's male given jeans. I'm going to ask myself, does that equal probability of, let's see, first thing, this one that goes here, that would be probability of male. Now you see why I asked those specific questions. So is 12 out of 20 the same as 17 out of 36? Well, no, it's not. So the answer to this, are gender and attire independent, is no. In this situation, if I know someone is wearing jeans, it is more likely that they are male. If I know someone is not wearing jeans, it is more likely that they are female. So knowing information like what they're wearing does influence whether or not I know they're male or female. It changes the probability. So the answer there is no, they're not independent. If I got something like 3, 6 equals 1/2, bam, those things are equal, I could say yes, the two variables are independent. So equal, independent. Not equal, not independent.